Alright, let's talk a little bit about question 6, which is this problem called Towers of 16. So here we see three different locations, each location with some kind of graph for cross-correlation. And just as a review, the peaks of each cross-correlation graph shows when did our device actually receive a signal from such a location. So for example, the signal from Gaussian Tower would be received at the 6th second, while the signal from the NVA tower would be received at the 1st second. So now let's barge into the question. Part A asks us how far away are we from each of the beacons. Here is a good place to remember the best treasure that humanity and technology has ever brought, which is that distance is equal to velocity times time. So as long as I know how fast my signal is, and when did the signal arrive, or how much time does it take for the signal from being emitted to arriving at my device, I can calculate the distance between my device and the signal emitter, which is the location, the towers we're looking at. For the Gaussian tower, the distance will be equal to the signal's velocity, which is 300 meters per second, times the second at which this signal from Gaussian tower arrived at my device, which is 6 seconds. So in that case, I'll be able to say that the distance is equal to 300 meters per second times 6 seconds. And this gives me 1,800 meters. Let's move on to the NVA tower and apply the same logic of arithmetics. I know that the signal from NVA tower should arrive at approximately 1 second, so this should be 300 meters. And last but not least, we're dealing with this charge tower, which has a distance of simply calculated velocity times time. This time I don't remember the time, so I must go back and check. I see that the peak of the cross-correlation graph is at the 3rd second. So I multiplied this by 3 seconds, and I get 900 meters as my distance. Now let's move on to the second part of the question, where the question asks us that if we have written a system of linear equations to try solving my location in the 2D space of this kingdom with the 3 towers, what matrix or vector should correspond most closely to the distances we found in the previous part? Say that we somehow came up with a matrix vector equation, that is AX is equal to B. Since we are solving for our location, X should be my location. This location vector will represent my coordinate, or the device's location. While both A and B are supposed to be the known parts of the system, it does seem like we should put the constants of these equations on the right side of the equation, since they are not multiplied by any coefficients. And I know that A is a matrix that has a lot of coefficients to multiply the unknown with to get the known value. And this known value is again the vector we see in B. And since distance is a known factor in this system of equation, we should say that B resembles most closely to the distances we found. And again, be careful that what we said is resembles most closely to this distance, because it could be the case that the vector B doesn't entirely accurately present the distances between our devices and other towers. It just should be the closest to what the distances are as a representation. Now let's move on to the final part of the question. We instead found these sets of distances between our devices and other towers, and now we're asked to try to figure out what our location actually is in this kingdom with the 16 towers. let's try reviewing a little bit about what we can do here. We know that each of the tower is located somewhere in a second dimensional real space. In particular, the Gaussian tower is located at 7, 2. So it should be somewhere around here. And I also happen to know that the charge tower is located at 0, 9, while the MVA tower is located at -2, -7. We know the locations of these three towers, and let's try to label them. We know that, for instance, we might be some distance from the MVA tower, might be some other distance from this charge tower, which means we could be on the edge of the circle, and at last we could be some other distance from the signal station that is 7, 2. So I'm again probably on the edge of this circle somewhere. This point where the three edges intersect tells me that I am simultaneously the amount of distance I want from all of these three signal towers, which means the three edges intersect at my location. Let's try to draw out this graph with a better representation. Use some different colors here. This point, that is, in this case, origin. But our actual point or location would not actually be the origin, and we have to calculate that out. But fortunately, we know that the solution should be the intersection of these three edges, and these three edges will happen to be a part of some kind of circle. To be more specific, it's the circle that is centered at the tower, and the radius of the circle will be the distance our device should be from the satellite station. So in this case, let's say that the distance from Gaussian tower, which is centered at 7, 2, is x minus 7 squared plus y minus 2 squared equals the square root of that distance, which is 18, as given from the problem. Now let's move on to a different tower. In this case, we'll first deal with NVA tower, and what we'll see is that the NVA tower, since it's located or centered at -2, -7, I'll have some kind of very similar equation that represents my circle. And in this case, the radius square will be 72, since the distance itself is the square root of 72. Last but not least, I have distance from the charge tower, which means that I would have a different circle that is centered at 0, 9, and so I will have x squared plus y minus 9 squared is equal to, this distance is supposed to be 116. You might have noticed that we could just write all of these circle equations in the form that they foiled out, but that's pretty tedious to write out, so I'm just going to write out that this system of equations could be solved, and it actually only yields one simple solution, which is that the location is x, y is equal to 4, -1, and that would be our actual location in the second dimensional real space. To solve out this system of equation isn't really too hard. We see that every equation we have here follows the form of x squared plus y squared minus some x minus some y, or in other cases could be plussing some x or some y, or in other cases could be just plussing or minusing one of the other. And last, adding some kind of constant is equal to our current distance. In this case, I'll have 4 plus 49, which is 53, is equal to 72. And here I'll have also 53, and then this is equal to 18. This system can be reduced into a system of two linear equations if we subtract each equation from each other. Unfortunately, all of these three equations, as a result of subtraction, will then converge to this solution that we have here. By doing some algebra, we'll be able to solve 6c.